Hi everyone, and welcome to this latest session of Geometry, Cosmology and Spirituality for today's new moon. It'll be happening in just under half an hour from now. Now, in today's session, we're going to look at the number 7. So I'll get going with the slides. In the first session, a few weeks ago, a month ago, I suppose, I talked about how 11 and 7 show themselves in the relationship between the Sun, Earth, and Mercury. Now, you may remember that I pointed out that if we look upon this circle here of 22 and 7, diameter of 7, circumference of 22, if we look upon each distance here as being 1 year, then 11 of these is the amount of time you get in the sun cycle. And after one sun cycle, the poles of the sun invert, so as in going from here to here, symbolically speaking, and then you have another 11 years before the poles then invert again. Now, the other line that we have here, this line of 7, over the course of 7 years, Mercury will have gone through 29 of its orbits, and 29 is, of course, 22 plus 7. So you have this sort of pi geometry or pi number occurrences with Sun, Mercury, and Earth. Because, of course, if we're talking about years, we're talking about an Earth cycle. Now, in the last session, 2 weeks ago, I talked about the Earth-Moon diagram, which was a remarkable diagram discovered by John Michell, or I suppose envisioned by John Michell back in about 1970. And this also involves the numbers 11 and 7. So you have a baseline of 11 and a height of 7 with the pyramid triangle. And this revolves around this circle, which is the size of Earth in relation to this one, which is the moon. Now, if we look at where that triangle actually occurs within the three-dimensional pyramidal form, as you can see, it's this one here. Now, the thing that I want to go to with this association of the number 7 is 7 as a relationship between heaven and earth. This is one of the really the key aspects of symbolism when it comes to the number 7. And you can see how we can look upon it in that way with the pyramid triangle, because you have this height of 7, which goes from the square of the square base of Earth, as it were, up to that apex, that heavenly focal point of the pyramidal form. So you have 7 as this relationship between the two worlds, and in the sense you have these 7 steps going from Earth up to heaven, or vice versa, coming down from above. Now, seeing as these are cycles based around the lunar cycle, we can straight away, we can see the number 7 with the moon itself. There are 2 lunar cycles that we talk about. The sidereal cycle is 27 1/3 days, and that's the amount of time it takes for the moon to go around the Earth. And then the lunar phase that we see with the phase of the moon, that takes 29.5 days. So you have 28 days as this, I suppose, archetypal number between those 2 cycles, and 28 it gives us these 4 7-day weeks, which and each 7 days is 1/4 of the moon. So 7 is there very prominently with this heavenly form that we can see from down here on the Earth, which reflects the light of the sun down to us. Now, perhaps the most prominent one with this association of 7 between heaven and earth are the 7 planets, as described in the ancient and medieval world. So you have these 7 steps, these 7 planetary steps between that which is above and that which is below. So it forms, symbolically speaking, a 7-step ladder through which the soul can ascend through the heavens. Now, with the embodied soul in mind, you also have the idea of 7 levels within the incarnate human form. The image on the left is Indian. It's a Kangra Valley miniature painting with the 7 chakras in the body, as described in the Tantric tradition. And then the image on the right, interestingly, is a European image. It's from 17th century, a Christian mystic called Gestell. And in this image here on the right, you can see how he's got the 7 planets within the body. So you have that idea of the ascent through the planetary spheres actually within the human form. Now, 2 more examples of this idea of the soul ascending through the planetary spheres. One on the left is an image of Dante, the Italian poet. And in his Divine Comedy, he first goes through the underworld and then up the mountain of purgatory. And then he ascends through these 7 planetary spheres. So even though it's an ancient storyline, it comes into the more recent religions, including this Christian example. Now, it's also in Islam as well, with the story of the Prophet Muhammad's Miraj, which is his ascent through the planetary spheres. So even though it's an ancient storyline, it comes through into more recent times. Now, another interesting Islamic example of 7 in the sense of it being a relationship between heaven and earth is with the letter A in Arabic, the Aleph. Now, in some of the proportioning systems of Islamic calligraphy, the Aleph is associated with being 7 units in height. Now, this image you're looking at here is from a book by my teacher, Professor Keith Critchlow, about proportional rectangles. And what Keith pointed out is that this sort of 7 units of height gives you 4 very significant mathematical ratios, which we use a lot in geometry. They're present within the geometric patterns that we draw. So they're there listed on the right there, and you can see the particular rectangular areas that are marked with those horizontal lines that have just gone in. So the first one at the bottom, the square root of 2, that's the ratio you find in a square. The short edge and the long edge of that rectangle are the equivalent of the edge of a square to the diagonal of a square. That's the relationship of the square root of 2. Now the next rectangle up, that's the square root of 5 plus 1 over 2, which is the golden rectangle, the golden ratio. The next one above that, the square root of 3 is what you find in the hexagon and the triangle. And finally, the square root of 5, which is the one that you get to the golden ratio from. Now, these 4 rectangles together remarkably make exactly 7 in their togetherness. If you put them together, they make exactly a height of 7. So the square root of 2 is this number here. And if we add that to the golden ratio, square root of 5 plus 1 over 2, we get the square root of 3 is the next one. And then finally, the square root of 5. And if we add all of these numbers together, we get exactly 7 to 3 decimal places, 7.00036. So they're all irrationals. So you're not going to get an exact 7, but you get 7.000, which is quite a remarkable concordance. Now, another Islamic example of 7 are the 7 circumambulations around the Kaaba, which Islamic pilgrims do when they go to Mecca. Now, I assume this is in emulation of the heavens because Muslims go anti-clockwise around the Kaaba, and the stars, as you can see in the image of the left, they go anti-clockwise around the celestial North Pole. And so in this sense, the stars of the 8th heaven are centered on the heavenly pole, whereas in the Islamic world, the Kaaba is the earthly pole. And you have this movement, as it were, through the 7 planetary spheres to the earthly pole of the Kaaba. So more of these sort of cosmological ideas concerning the number 7 and an ascent through 7 levels. Now, another example of this is the education in the medieval universities in Europe. The 7 liberal arts were the 7 subjects that were taught, and they were associated with the 7 planetary spheres. And the association was that you would learn these 7 subjects, and then when you reach the 8th heaven, you're then ready to study philosophy. And so here you have an image on the right of Lady Philosophy with her ladder. This is a character from Boethius's Consolation of Philosophy. Now you can't see it, it's very small, but on each of the rungs of the ladder, each of those 7 rungs is a name of one of the 7 liberal arts. So through this educative ascent, as it were, one is then able to enter into direct relationship with Lady Philosophy herself, who is up in the 8th heaven. Now, another Christian example of 7 is the 7 gifts of the Holy Spirit. And the 7 gifts are also associated with the 7 planetary spheres, according to St. Irenaeus, who's a very early Christian father. Now, the 7 gifts of the Holy Spirit descend on Pentecost, and Pentecost is 7 times 7 plus 1. It's 7 times 7 days, not 7 times 7 weeks. I got that one wrong. So 7 times 7 days gives 49, plus 1 day is the 50th of Pentecost. Now, another Christian 7, and this is associated again with the Virgin Mary, who one of her numbers is the number 7. This is the Abingdon Labyrinth, which consists of 7 circles, and it's about her assumption through the heavens. So again, there's another relationship between heaven and earth in terms of her assumption, her ascent. And there's a verse written in the labyrinth which includes these words here: "Wisdom has structured this city which a sevenfold circle surrounds." Now, with the Virgin Mary in mind, the number 7 to the Pythagoreans was known as the number of the Virgin. Now, this is often mentioned, but I'm going to actually describe it in detail because it's quite interesting the way it works. Now, first of all, the decads are the numbers that the Pythagoreans dealt with, the first 10 numbers. But the number 1 wasn't seen as being a number. That's rather the principle of all number. So if you multiply 1 by itself, it doesn't change. It just remains as 1. Or if you multiply any number by 1, the number doesn't change. So 1 is beyond that generative sort of multiplicitous nature of number, and it's just 1. It's at the beginning. It's the principle of all number. So number 1 doesn't feature in these particular calculations we're going to look at relating to the number 7. So we have to begin with 2. Now 2 times 2 equals 4. Now there we have the parents and offspring. So you can say that the 2 numbers that are multiplied are the parents, and the number that is calculated is their offspring. So here we have 2 times 2 equals 4. Now let's go to 2 times 3 equals 6. 2 times 4 is 8. 2 times 5 is 10. Now, all of these are valid because all the numbers that they contain, parents and offspring, are all within the decad. They're all within the first 10 numbers. Now, if we went to 2 times 6, that obviously equals 12. And so we can't have that calculation because 12 is beyond the decad. So we stop with all of those various calculations of 2. So let's go to 3. Now, 3 times 2, well, we already have that here with this second calculation. 3 times 3, we don't have that one. So 3 times 3 equals 9. Now, if we go 3 times 4, that would take us to 12. So again, we can't have that calculation. So let's now start with the number 4. 4 times 2, well, we already have that one on the left there. 4 times 3, that takes us to 12. So that's the last one we can do with 4. Let's begin with 5. 5 times 2, we already have that one. 5 times 3, it's 15, so we can't have that one. Now on to 6. 6 times 2, well, that gives us 12 straight away. So these are the only calculations, these 5, where parents and offspring are within the decad. Now, if you look at all the numbers that are there, as I said, 1 isn't used, but you have 2, 3, 4, 5, 6, no 7, 8, 9, 10. And so hence 7 having this particularity about it. It's the only one that doesn't feature. And so in the words of Iamblichus, who wrote a book called The Theology of Arithmetic, by mingling the number 7 with any of the numbers within the decad, it does not produce any of the numbers within the decad. Nor is it produced by the intercourse of any of the numbers within the decad. They called the heptad Athena because it is a virgin and unwed, just like Athena in myth, and is born neither of mother nor of father, but from the father of all, the number 1, the head of number. Right, let's get down to some drawing. So I shall stop sharing my screen. Right, hello everyone. I thought I should say hello before I start drawing.
We're allowed
Thanks for
to
joining
ask
me
questions,
this
or
morning. I wasn't sure how many people would come. Obviously, it's not 9 o'clock in the morning everywhere, but thanks for coming. So I shall switch on my drawing camera. Right, and I'm going to try and pin my camera for everyone. Okay, right. Right, now what we're going to do is divide a circle into seven, but the way that we're going to do it is a way that I've not actually seen done before. I just sort of worked it out after after the session a few weeks ago when we did the 11-fold division of the circle. We used a rational division. We took the radius, divided it into half, and then divided that half into 8, and then added 1/8 on. Now you can see that in the first one of these sessions, so if you want to see that in detail. Now I looked at some of the radius to edge relationships of the polygons. And I noticed that you can do something similar with the number 7 as well. So that's what we're going to look at. And it involves, interestingly, it involves numbers that relate to the number 7 as a mean. So it's quite a nice use of the numbers themselves. So what I'm going to do is get us first to get a radial measurement. Now the radial measurement that we need is 3 3/4 inches. Now I'll describe this particular measure shortly once we've got it. Right, so as you can see, when I was counting there, what I was doing was counting quarter inches, because this is the way that we actually get the relationship. The relationship is that if the radius is divided up into 15 units, then what we do is reduce the compasses to 13 units, and that gives us the 1/7 of the circle. Now, where 7 acts as the mean in this way is if we halve 15 and 13, we get 7.5, 6.5. So we begin, you could say, with 7.5 and reduce to 6.5. And of course, the mean between those two numbers is the number 7. So that's quite a nice feature of this. But I'll talk more in terms of 15 and 13 because it's just a bit more straightforward because they're whole numbers. So as you can see, these quarter inches, 1, 2, 3, 4, 4/4 inches in 1 inch, obviously. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 quarter inches, or 3 3/4 inches. Right, find the central point of your page. No ruler needed for this. I'm just going to put the point of my compasses into the top of the circle. So get that into that top point. Just judge it by eye. Don't worry if it's exactly there. My teacher, Keith Critchlow, would always encourage us to use our sort of innate sense of geometry when we were drawing. Now, what I'm going to do is reduce this radial measurement from 3 3/4 inches to 3 1/4. Like so. So as you can see, if I count those quarter-inch units again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we reduced from 15 quarter inches down to 13 quarter inches. Right, now we'll go into that point at the top of the circle that we marked a second ago. And draw an arc like so. If you saw the session that I did a month ago, where we divided by 11, you may remember that I went down one side of the circle and then came back to the top and went down the other side. And that's just a useful thing um, to stop what's known as accumulated error. So if you keep on, because this isn't absolutely precise, it's not actually possible to divide a circle into seven precisely. This is another thing about the number seven. It's very elusive. It's out there on its own, and it won't allow itself to be contained, as it were. It's a mysterious number, the number seven. So as you can see, I did that first arc and then put the point of my compasses where that arc reached the circumference, and that gave me this arc. And then I went from the end of that new arc to do that. Now at this point, so I'm going to go back up towards the top on this side of the circle. I'm going to place the point of my compasses here, and I'm going to come down in the same way. It gives a really good, accurate division. Right, as I did a month ago when we did the 11 and the 22, I'm gonna put pinprick holes through, well, the 7 points in this instance, and then we can turn the paper over. There's two different 7-pointed stars, and I'm going to get us to draw both of them. So I think we'll go through this process twice. Now I might as well mark these points so you can see them. And then it'll make a bit more sense of the process that I go through. So 1, 2, 3, 4, 5, 6, 7. Now, if we were to go from one point to the next, then we'd just get the heptagon, the seven-sided polygon. So to get the polygon stars, we need to skip a point, as it were. So I'm not going to go to this one. I'm going to skip a point and go to the one after. And I'm going to keep on following that principle. So I'll skip this point and go to the next one here. And keep on following that one. And then you start to get this dance, as it were, where it keeps on moving around until it returns back to its origin. So here is the first one of the seven-pointed stars. Now it has the sevenfold polygon at the center of it. So it contains that first initial shape that you get. Right, let's go through the process again and we'll draw the other seven-pointed star that time. So let's go back. Oh. Now, it's always good to repeat these processes because then they really become ingrained in you. So we'll go right back to the start. So we'll need to reset our compasses back to 1, 2, 3 and 3/4 inches. So that 15 quarter inches. Center of the page and circle with that radius of 3 3/4 inches. Now, perhaps I'll take this opportunity to explain exactly why this works. The relationship of radius to edge within a seven-sided shape is this. If the radius is 1, then the edge is 0.86776, and it would just go on and on. It's an irrational number. Now, what I've done by having this 15 to 13 relationship is this. If the radius is 1, then the edge is this 0.86666. So you could say that 1 unit is 0.66666, and 2 of them are 1.33333. And so 1 takeaway 1.33333 is this. So you can see how similar it is to the actual precise 1/7 of a circle. So this is why it works. And this seems to be one of the things that happens in the ancient and medieval worlds, that they have these rational approximations of irrationals. So the numbers which are essentially, I suppose, ultimately unknowable, they're unbounded, or you could say they're numerical reflections of the unbounded. They become bounded through becoming rationalized. And in that sense, I suppose they take on the boundaries of the earthly world, but ultimately they're beyond boundaries. They can't be fully known by the human mind. And that's why they're known as irrational. So they're without ratio. Now let's go back to our ruler and reduce again to 3¼ inches. So 13/4 inches, or 8, 12, and 1 is 13. Now back up to the top. And once I've got down to here, I'm now going to go back up to this side on the left. Now, accumulated error is obviously always an issue because this isn't exactly the same as this. So that's why it's worth going down equally on both sides. Because if you keep on going around the same way, if there is any inaccuracy, slight inaccuracy, it builds up more and more and more the more you go around. So that's sort of the rationale of going down on both sides. And that's just a beautiful form in and of itself, even before we draw the star. Ah, forgot to put the pinprick holes in. So yes, at this point, put in the 7 pinprick holes. You don't need to put in these marks here. I'm just putting them in so that you can see what I'm doing on my drawing. But if you could see your pinprick holes, that's all you need, really. Right, so you remember I said about the last one, that would be a polygon if we just went from one to the next. What we did last time was to miss one and go to the next one. Miss one, go to the next one. So this time we're going to miss 2 and go to the next one. Now, if you think about it, this is the only other thing that we can do, because if we say miss 2 in the other direction, one, two to here, we just draw the opposite line, which you're going to be drawing anyway. So this is the only other star that we can do. Miss 2. And this star is more stellated. Now you can see this star contains everything else. So this is the star that we just drew a few minutes ago, which itself contains the heptagon at the center of it. So this final star is one that contains all of the previous forms as well. Now, at some point, perhaps I'll go into detail about this whole principle of polygon stars and how they develop within all the shapes as you develop, because there's a certain number of stars that you get for each polygon. There were, I think, when we did the 22 pointed star a month ago, I think there's 9. I think I pointed out that there's 9 different stars you can do there. So obviously the more numbers you have in your division of the circle, the more polygon stars you can get. But there's also certain patterns you get with how sometimes there might be a weaving star, say such as these 2 7-pointed stars, where it just weaves around itself and returns back to the starting point. But sometimes if the number isn't a prime number, for instance, then you'll be able to have, say, 2 stars. So for instance, 14 isn't a prime number because you can divide it by 7, by 2. And so if you had another 7-pointed star with its point pointing down, you'd have a 14-pointed star made up of 2 separate 7-pointed stars. So there's a whole thing around that. So perhaps I'll go into that at some point. Right. Okay, everyone. I'm going to go back to my camera. Right. I hope you enjoyed that. It's really good to wake up to a bit of geometry as well as having some in the evening. Now, the next one will be, well, on the full moon in a couple of weeks' time. In fact, again, it's Monday morning and it'll be at 9 o'clock. So it's a very similar time in 2 weeks' time when we'll next meet. So do come along again. I hope you've enjoyed this session, and I shall see you in a couple of weeks' time. Goodbye.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Thank you. Thank you.
Thanks.